Hi, my name is Simrah Waseem, and today I will be presenting my Project 5 to you. So, the first reaction that we'll be looking at is step 2 in the formation of acetylcholine chloride by nucleophilic acyl substitution. More specifically, it is a reaction in which the acid chloride is converted to an ester, in which the chlorine acts as a leaving group and is substituted by the ROH group over here. The first step in a nucleophilic acyl substitution is the attack of the carbonyl-carbon atom of an acyl derivative by a nucleophile. So this is the nucleophile, and this attacks the carbon over here, and then the electrons from the pi bond move up to the oxygen, forming an anion. When this attacks over here, after the nucleophile, this is the cation. And the first step is the rate determining step, and the ROH group acts as a nucleophile to form the intermediate. And the oxygen anion can then pick up the hydrogen from the ROH cation, and then you form a neutral molecule. And after this step, you remove the chlorine and form a pi bond by moving electrons from a lone pair on oxygen, which gives this oxygen a positive charge. And then something in the mixture, most of the time, we use pyridine is used to remove a proton on the protonated oxygen and form an ester. So this ester over here. And since chlorine is the leaving group, the elimination of the leaving group allows for a carbonyl reformation, thus completing the substitution reaction and forming acetylcholine chloride. So the next reaction that we'll be looking at is step 3 in the reaction formation of azapentene. And this is a reduction reaction of an amide using a lithium aluminum hydride as the reagent. And the nucleophilic H from the hydride reagent adds to the electrophilic carbon of the polar carbonyl group of the amide, and electrons from the carbon-oxygen double bond move to the oxygen, giving it a negative charge. This happens for both of these carbon-oxygen double bonds that we see over here, and giving it a negative charge, and this creates a tetrahedral intermediate, and then the tetrahedral intermediate displaces the oxygen, forming a double bond with NH, and this forms a highly reactive iminium ion, and the nucleophilic H from the hydride reagent adds to the electrophilic carbon and reduces it. Pi electrons from the carbon-nitrogen double bond move to the cationic nitrogen, which then neutralizes the charge and creates our amine product that we see over here. Next, the reaction that we'll be looking at is the formation of balinostat, and this is a nucleophilic acyl substitution as well. And first, the methoxy group acts as the OR group and is substituted by OH, and then this step that I drew in the middle over here is actually not drawn on the pharmaceutical substance bank. However, I choose to draw it anyways because it helps us understand the reaction better and makes what is happening in the reaction clearer. So then the OH group from here is substituted by chlorine using COCl2 as the reagent. And the mechanism of nucleophilic acyl substitution. So basically, I'll be explaining the mechanism for this for the first step of the reaction. And when going from an OR group to an OH group, we use an H plus to protonate the ester. And once the ester is protonated, the neutral nucleophilic water can add, forming the intermediate. And we want the oxygen in the OR group to leave and not the oxygen in the H2O that was just added. So we want the oxygen over here, we need the OMe group to be the leaving group. So in order for this to happen, we have to protonate OMe because to make it into MEOH, which will make it a better leaving group. And once then one of the two OH can assist the cleavage of the protonated oxygen on MEOH by forming a double bond. And once the leaving group MEOH is gone, then anything with a lone pair electron, other than we can even use the MEOHs that just left, or water can act as a base to remove a proton and form this product over here. And a similar mechanism is followed when we go from step 2 to step 3, in which again we want to remove this to form and we want to remove this and have chlorine be substituted in for OH. So yeah, this basically, it will follow a similar mechanism to get here to give us this final product that we see. So next, I'm going to be talking about the formation of benazepril, and This is step 3 in that reaction, and this is an SN2 reaction. So an SN2 reaction is a bimolecular nucleophilic substitution. Overall, it is a second order reaction, and in SN2 reactions, the ability of a reagent to donate an electron pair to another atom is known as nucleophilicity. Nucleophilicity depends on the substrate, the solvent, and even the reactant concentrations. There are two types of solvents, nonpolar and polar solvents, and then there are two types of polar solvents, polar aprotic and polar protic solvents. DMSO, which is being used in this reaction over here, is a polar aprotic solvent, and the best solvent in SN2 reactions are polar aprotic solvents, like DMSO, and this is because they have strong dipoles but do not have OH or NH groups. Polar aprotic solvents are used to solvate metal cations rather than nucleophilic anions, and this results in naked anions, which makes the electron pair of the nucleophile more available. In this reaction, DMSO solvates the sodium cation, and then so we have NaN3, so the sodium cation is solvated by DMSO, and then N3 acts as a nucleophile and chlorine acts as a leaving group, thus giving us our product. So chlorine acts as a leaving group, and N3 acts as a nucleophile, and we get our product over here. So the next reaction that we'll be looking at is the formation of benzathine benzyl penicillin, and this is a hydrogenation of an alkene in which syn-cis addition of hydrogen occurs across a double bond. This is slightly different from the mechanism that we have talked about in class, which occurs over a carbon-carbon double bond, whereas this is a carbon-nitrogen double bond. However, since it follows the same process, Professor Chem said that it would be okay to use this reaction. Next, we'll be looking at step 1 in the formation of biotin, and this is a halogenation reaction. As you can see, this is a halogenation reaction that adds bromine by anti-addition on the double bond over here. And the mechanism in this reaction is that the BR-BR bond in Br2, so the BR-BR bond becomes polarized when it comes close to an alkene and forms a brominium ion. Then bromine is added again to complete the reaction, forming the meso compound that we see over here. Now, the interesting thing about meso compounds is that they are mirror images. So they are symmetrical, and the mirror image of meso compounds are superimposable, and they are optically inactive despite having stereocenters. So next we'll be looking at still the formation of biotin, but this is step 6 in that reaction, and this is a unimolecular elimination reaction, also known as an E1 reaction. All nucleophiles are potential bases, and all bases are potential nucleophiles. Substitution and elimination reactions are always in competition with one another. Different factors can affect which type of reaction is favored. Sulfuric acid over here acts as a base, making this an elimination reaction. First, the leaving group OH is protonated by H2SO4, which makes it a better leaving group. Once it leaves, it forms a carbocation. Then a proton is removed by water that acts as a base, and this gives us an alkene that we see over here. And the loss of a leaving group is also the first step in an SN1 reaction, which is why SN1 byproducts may be observed. Next, the last reaction that we will be talking about today is the formation of captopril. And this is step 2 in that reaction. And this is a nucleophilic acyl substitution in which the carboxylic acid is converted into an acid chloride. And the OH on the carboxylic acid is substituted by chlorine. And carboxylic acids can be converted to acid chlorides but react with thionyl chloride. Thionyl chloride is the reagent that is being used in this reaction. And during the reaction with thionyl chloride, the hydroxyl group of the carboxylic acid is converted to an acyl chlorosulfite, which acts as a better leaving group. And then the nucleophilic chloride anion is produced, which reacts with acyl chlorosulfite, and through nucleophilic acyl substitution to produce an acid halide that we see over here, acid halide, acid chloride. Since thionyl chloride only reacts with carboxylic acids, the other ketone that we see over here does not react with thionyl chloride. And so this concludes my presentation. I hope you enjoyed it, and yeah, bye.